All right, now we're going to move on to talking about normal vectors. This is the second type of vector that we're interested in computing in this section. We had this theorem back in section 2.2, and it becomes extremely important here in this section. Notice that it said that if r of t was a differentiable vector-valued function in 2-space or 3-space, and if it was the case that the norm of that vector was constant, so like at every single possible value of t, I always get the same length, then if I take that vector function dotted with its derivative, I should get 0. Keep in mind that if the dot product of two vectors is 0, that means that the vectors are going to be orthogonal to each other. Well, using this theorem is actually really useful. Keep in mind, capital T of t was our unit tangent vector. Now, I could evaluate this unit tangent vector function at a specific point, like we did back in example 1. But if I didn't evaluate it, if you imagine I did this full calculation here by not plugging in for t at any point in time, then I would have ended up not with a vector with all numbers, but with a vector function with the variable of t in it. And that vector function still would have been always a unit vector. It would have met this condition. It would have been length 1. That's what I state down here. Since t of t is a constant norm, because the norm of this is constant, it's a unit vector, then the derivative of this would have to be orthogonal to it. And this leads us to the following definition. Provided that t prime of t is not the 0 vector, we call t prime of t a normal vector to the curve, meaning it's going to be orthogonal to the tangent vector at that point in time. And we would actually then define capital N of t as the derivative, so this normal vector, divided by its length, to shrink it down to be a unit vector. We refer to this specifically as the principal unit normal vector. Okay, so here's the kind of the general idea. Think about if I was working with this in 2-space. So imagine I have this curve here in 2-space, C, and I stop at this point right here, and I could measure out my t of t, my unit vector. Well, I know that the normal vector that I could create would have to be orthogonal to it. However, if I look here in the picture, I could see that there are actually two different vectors that I could draw that would be orthogonal. The case gets even worse when I look in 3-space, because if I was in 3-space and did the same thing and I still had this vector t that was the tangent vector, in 3-space I can actually rotate almost in any direction and always be perpendicular to this vector t. And so there's actually infinitely many normal vectors that I could create. So we have to kind of state here that we're dealing with what we call the principal unit normal vector, meaning that we're actually only going to be able to classify one of these vector choices as the unit normal vector. So when we say n of t, we actually mean specifically this guy in 2-space. And I'll talk a little bit more about how I would know exactly which guy in the picture I'm working with. Okay? And in 3-space, things are a little bit harder to determine. But I should note that there are actually many normal vectors and that I am only going to be able to work with just one of them. This is actually extremely similar to kind of the way that we think about square roots. Like if I was to actually ask you what is, I should be careful about how I write this. If I asked you for like what is the square root of, say, a number like 25, technically there are two answers to this. There's positive 5 and negative 5. However, if it is the case that I ask the question looking like this, there is only one answer, and that is 5. And that's because when we write this square root symbol, that's a way for us to indicate that we're talking about the principal square root. That is like the one of the two options that we are actually always going to refer to as the square root. And this is why, like when you actually graph the square root function, we only ever get positive values out. If we got negative values too, then it wouldn't be a function. So we're kind of using this similar language here when we talk about the fact that there could be multiple normal vectors. So how do we go about finding these normal vectors? Well, we'll talk about that in example 2 in the next video.